All right, so let's look at our first example. We want to compute the surface integral of the curl of f dot ds. That should have a hat on the s there, where f is this vector field and s is the portion of this paraboloid below z equals 4. We are assuming upwards orientation. In the homework, if the problem doesn't specify, then the assumption is upwards orientation. So I thought we would work this out direct without Stokes' theorem first, both as a review of how one computes surface integrals of vector fields, but also to confirm that Stokes' theorem does indeed work. So if we're going to do this directly, we're going to need to begin by computing the curl of f. And I'll let you do that on your own. If you'd like to pause the video and work that out, you can. But the curl of f is just x minus 2y, x minus y, and 0. So that's the first thing we want to do. This is the vector field we're going to work with now. And then second, we want to find a parameterization for my surface. Well, again, your surface is given to you by some equation z equals a function of x and y. So you know what to do. We're going to use r of x and y is the parameterization. X is x, y is y, and z is x squared plus y, and we want this to be on whatever the projection of my surface is down into the xy plane. Well, you can see it's going to be the circle x squared plus y squared equals 4 because you're going up here to z equals 4. So this is going to be on x squared plus y squared. We want the full disk, so we'll say less than or equal to 4, and I've gone and drawn that down there. So we'll call that region D. We want to compute, not in highlighter, we want to use a pen. We want to compute Rx cross Ry. Hopefully you've kept this in your back pocket. It's really nice to be able to work this out quickly. So I know I'm going to get minus 2x minus 2y1. Formula, again, this is my g of x. And so I know in this case, r partial x cross r partial y is negative g partial x, negative g partial y 1. And check that here 1 is going to be positive in the z direction, giving me the upward orientation that I want. If for whatever reason you wanted the negative orientation, you would do exactly the same thing, but you would just hit this thing with a negative. So you would have plus, plus, and minus. You can certainly change it if you want to. All right, I think we have everything we need now to compute this integral. So here we go. The surface integral over our surface S of the curl of f dot ds. Straightforward, no Stokes theorem. This becomes the double integral over the region D of take the curl of f and plug in your parameterization. In this case, nothing changes because there are no z's in the curl of f. And so z is the only thing that changes. And so I just write down the curl here, x minus 2y, x minus y, and 0. Again, typically you're plugging in your parameterization, but nothing changes. Then I'm going to dot this with negative 2x, negative 2y, 1. That's my r partial x cross r partial y. I'll take that dot product, and I get maybe we'll put an arrow there so we can read this. I get the double integral over d of negative 2x squared. Then I'm going to get plus a 4xy, then minus a 2xy plus a 2y squared, and then plus 0. So we'll leave that off dA. All right, so we can combine these like terms right here, and let's go ahead and do that. I'm also going to just rearrange things a little bit. So I get the double integral over d of, let's view this as 2 y squared minus x squared plus 2xy dA. So now I'm back to just doing double integrals, and I'm working over a circle, so I'm very much motivated to try and switch this thing to polar. This one doesn't maybe simplify as much as we might like, but let's still make the switch to polar. This is circular radius 2, so r goes from 0 to 2, theta from 0 to 2 pi. And what do we get? We get a 2. Here I'm going to get an r squared sine squared minus an r squared cosine squared. Let's pull the r squared out. So we get a 2r squared, and then we're going to have a sine squared theta minus cosine squared theta. I'm going to need more room. Let's just drop this down right here. And this is going to become plus another r squared because I have a r cosine theta, r sine theta. So plus 2r squared cosine theta sine theta all times r dr. Let's just cube these r's, and now we've worked in that r dr, and then we can just say dr d theta. We worked in the extra r, excuse me. All right, so at this point, I'm going to recognize a couple of things. I can pull the 2r cubed out if I want to, and I'm also going to recognize that, hey, sine squared minus cosine squared is the same as cosine of 2 theta. It's really nice to know those trig identities. If you don't know them very well, you'll certainly want to reference them when you get a problem like this and just see, hey, is there a trig identity that would help me clean that up? So I can write this as 2r cubed times cosine of 2 theta plus cosine theta sine theta, and this is all dr d theta. I'd like to squeeze this in without having to stop and move everything, so let's just go right here. You can write this, I'm going to break this up now as the integral from 0 to 2 of 2r cubed dr times the integral from 0 to 2 pi of cosine of 2 theta plus cosine theta sine theta d theta. Now, I'm going to tell you, without working out the details, that when you integrate from 0 to 2 pi over cosine of 2 theta, you get 0. This one is pretty easy to see. The integral of cosine of 2 theta is sine 2 theta over 2. Plug in 2 pi, you get 0. Plug in 0, you get 0. So that one's easy. This one is one you've seen enough. In some ways, you should know it, actually. It's really nice to just know this one. But if you don't, you do a basic u sub, and it all works out. So let's realize that this integral is going to give me 0. 0 times whatever this is. The whole thing is just 0. It really wasn't horrible to do it directly. It took some work, but we worked it out, and we got 0. So now let's work it out with Stokes Theorem and see how it goes. So let's realize that Stokes Theorem tells me that the curl, the surface integral of the curl of my vector field f, is the same as the line integral. We're back to line integrals of not the curl of f anymore, but f itself. Now that's an f, not an e, dot dr. So to work it out this way with Stokes Theorem, I need to parameterize the curve C. So let's begin by writing that down. We need to parameterize our space curve C. And if you think about it, and in this case, it's really not too bad. You know that your z is constant. Your z is always 4, and you just want to go around a circle of radius 2. So right away, you should be able to come up with r of t equals 2 cosine t, 2 sine t, comma, z is always 4. I want my t to go from 0 to 2 pi. I'm going to stop and think about orientation. This is really important, and this is where our students can get very confused. It's not a huge deal to get it right, but you've got to check it. So we oriented our surface upwards, and so that means whatever parameterization I pick for my curve should take me around this curve in the counterclockwise direction where this is up. And so if you check, this parameterization does do that, but do check, do think about that and make sure that it's moving you in the right direction. So we'd better go up and copy our vector, whoop, we don't want to do that, copy our vector field f, that way we can remember what it was, because I've forgotten by now. So here's our f, and we'll scroll down and we'll just plop that right there. Let's make it maybe bright pink so that we don't think it's part of the problem. Okay, so now I'm interested in the line integral along C of f dot dr. And at some point with these problems, it just clicks. When you're integrating with vector fields, whether it's line integrals or surface integrals, it's always plug in the parameterization, multiply by a certain derivative as a dot product. So plug in the parameterization, dot product with the derivative. And I'm going to get the integral from 0 to 2 pi. Let's go ahead and write down, I'm going to get f of r of t, and I'm going to dot this thing with r prime of t dt. That's the general formula. Ooh, I didn't leave myself much room, did I? Let's work it out. And so we're going to get, maybe I'll put it right here, we're going to get the integral from 0 to 2 pi of f of r of t. Okay, z is always 4, so you're plugging this parameterization into f, so you're going to get, what, 8 8 cosine t, and then you're going to get, let's see, 2yz. So that's going to give me what? A 2yz is going to give me 416 sine t. And then I'm going to get, let's see, the last part, xy, gives me a 4 cosine t sine t. And now I want to dot this thing with r prime. I didn't compute r prime, but you can certainly do that with me. And you're going to get, what, minus 2 sine t, comma, then you're going to get a 2 cosine t, and then you're going to get just 0, so that's nice, that goes away. And so let's, maybe we need some more space here to work this out, so we'll just drop this down. So, oops, let me just copy all of this, sorry about that, and we'll move that down. Okay, so when I take the dot product here, I'm going to end up with, let's see, I'm going to get 0 to 2 pi, and then I'm going to get negative 2 sine t times 8 cosine t. That's going to give me negative 16 sine cosine. Here I'm going to get 2 cosine t, 16 sine t, so 32 sine cosine for a grand total of, let's just put those together, and we're going to get 16 sine t cosine t, because we had a positive 32 and then we had a negative 16, so 16 sine t cosine t, and then just 0, and again we're going to get dt. That's it, everything else falls out. And we already did this integral last time. It really pays to know that, pop the 16 out, when you integrate sine t cosine t from 0 to 2 pi, you're going to get 0. So we get the same thing. Now, in this case, our work was certainly shorter when we used Stokes' theorem. I'm not going to say that it was that much easier, but I think it was easier. The point isn't so much that it has to be easier in this example. The point is this is a tool in our toolbox that we can use when we need to. So let's break this video here, and in the next video, we'll work out